Hello everyone, welcome to lecture 16. In this lecture we will continue our discussion regarding the modes of operations of block ciphers. Specifically the roadmap for this lecture is as follows. We will discuss how to design efficient CPA secure ciphers using two of the modes of operations, namely the output feedback mode and the counter mode of operation. So, let us start with the output feedback mode or OFP mode in short. So, the idea here is basically sender and receiver generate a pseudo random stream of pad which is actually independent of the plain text which sender wants to encrypt. And once the pseudo random stream of pad is generated and the message is available, the pseudo random stream of pad is used for XORing or masking the message. So, let us see how the pseudo random stream of pad is generated. So, we start the sender randomly choose an IB which we denote as Y0, and the size of the IB has to be the same as the block length of your underlying function f. And then imagine we want to generate 3 blocks of pseudo random stream of pads. Here is how we go. So, we invoke 3 underlying invocations of the function f, all instantiated with the same key k, and we feed the IB as the block input for the first invocation, obtain the output y1, and then we do the chaining. But now this chaining is different from the CBC mode of encryption that we had seen in the last lecture. Here the chaining is independent of the message block, because as of now there is no actual plain text which is getting involved here. So, the output y1 is fed as the block input for the second invocation of the function to obtain the second block of pseudo random stream of pad which we could denote as y2, and then this is fed as the block input for the third invocation, and we can continue like this, right. So, this is how the pseudo random stream of pad is generated. And now if the message is available for encryption, whatever pseudo random stream of pad that has been generated till now, it can be used to mask the message depending upon the length of the message, right. So, you can imagine that the encryption here is now a 2-stage process, an offline process and an online process, where in the offline phase or a message independent phase, a pseudo random stream of pad is generated, and during the online phase when the actual message is available, we do the encryption by using whatever pad that has been generated in the offline phase as the mask, right. So, if the IB is also communicated to the receiver end, and the receiver also can generate the pseudo random stream of pad offline, and once the message is encrypted from the sender side and communicated back to the receiver, it can be decrypted properly. So, in this specific example, the encryption of the message will consist of the IB and the actual encryption, namely C1, C2, C3, right. And to decrypt, we do the corresponding operation, namely to recover back the ith plain text block. What we do is we also need, the receiver needs the ith block of pseudo random stream of pad, and which can be computed by just doing this operation, and once the ith block of pseudo random stream of pad is available, it can be XORed from the ith cipher text block to recover back the plain text. That means it is sufficient in this mode of operation for the f being just a pseudo random function. We do not need the function f to be an invertible function, that it suffice for fk to be just a PRF here. And the advantage of this mode of operation is that the stream can be pre-computed, and once pre-computed, the cipher text computation is parallelizable. That means we cannot generate the stream of pads in parallel, because the pad generation happens sequentially, but once the offline phase is over and the pad is available, whatever message block we want to encrypt, the encryption can happen in parallel, right. Moreover, another advantage here is that the plain text need not be a multiple of the block length of your underlying function f. That means here we do not require any sophisticated padding to make the length of the message to be a function of the to be a multiple of the block length of your underlying function before encrypting the message, right. So, this is unlike your CBC mode of encryption, and it can be proved formally that if your underlying keyed function fk is a secure PRF, then this mode of operation, namely the OFP mode, is CPA secure. Also, we can prove that the stateful variant is also CPA secure. That means, imagine a scenario where sender and receiver are synchronized and they have generated a pseudo random stream of pad y1, y2, y3, and which is used to encrypt say message m, right. And now there is a new message m dash for encryption which is available for the sender. So, if the sender now wants to encrypt the message m dash using the OFP mode, there is no need to pick a fresh IB. The Y3 which has been used which was the last block of the pseudo random pad for the previous message can be used as the IB for the message M dash, and using Y3 we can kickstart the whole process and generate a fresh pseudo random stream of pad which can be then used for masking the new message M dash, and it can be proved that the the stateful variant of this OFP mode is also CPA secure, right. So, more or less we actually get all the advantages that we want or we expect from the best possible mode of operation, namely now we have CPA security, we have the minimal assumption required from the underlying function, namely TRF assumption, and if we assume that the pad has been generated in the offline phase and the ciphertext computation is parallelizable and so on. But it turns out that we can do better, right, and that further better mode of operation is the counter mode of operation or the CTR mode, and the idea here is more or less the same, namely we divide the encryption process into two phases. The first phase is the message independent phase where a pseudo random stream of pad is generated and which is later used to do the actual masking of the message. But now the way the pseudo random stream of pad will be generated, everything can be parallelized. That means the pad generation as well as the actual encryption can be made parallelized. So, here is how this counter mode of operation is executed. So, as in the OFP mode we start with a random IV which we call the counter, and the counter is selected randomly from the domain of the block length of your underlying function. So, it is a uniformly random bit string of length big L and which will be also a part of the ciphertext, and then we generate the pseudo random stream of pad, but unlike the OFP mode we do not do any chaining here. The way we generate the pseudo random stream of pad is as follows. So, the first invocation of your function f will be with the input counter plus 1, the second invocation of the function will be with the input counter plus 2 and so on. That means, all the subsequent invocations of the function will be with an input which is one more than the previous value of the counter used in the previous or the previous invocation of the function f. And once the function f's are evaluated on this input, we get the pseudo random stream of blocks of pads which can be later used to actually mask your message for the encryption, right. So, that is the only difference here, the way we are generating the pseudo random stream of pad, remaining all the operations remain same as in the OFP mode here. So, here again the actual encryption of the message will consist of your counter value which will be the C0 block, and the actual encryptions blocks or the encrypted blocks will be C1, C2, C3. Okay. So, as in the OFP mode we can actually formally prove that it suffices for the underlying keyed function to just be a PRF to have the counter mode of operation to be CPA secure, because for the decryption purpose we do not require any inversion to be computed. So, that is why it suffices for the underlying keyed function to be just a PRF. More importantly, the encryption as well as decryption can happen in parallel. This is because if you see closely the way we are generating the pseudo random stream of pad, if I want to generate Y2, I do not need to depend on Y1, which was the case in the OFP mode. In the OFP mode, until and unless you generate Y1 you cannot compute Y2, and hence until and unless Y2 is computed you cannot generate Y3 and so on. So, that is why the pseudo random stream of pad generation that was not parallelizable. But the way we are generating the pseudo random stream of pad in the counter mode of operation, Y2 can be generated independently of Y1 and so on. In that sense, both the encryption and the decryption operation can be parallelized, right. More importantly, in the counter mode of operation, if I want to just decrypt a specific ciphertext block and I am not interested in decrypting the other blocks, that is possible, and that too by just invoking one invocation of the underlying keyed function. For instance, if I just want to decrypt C2, for decrypting C2 what I need is Y2, and Y2 just requires me to invoke the underlying function on the value counter plus 2. So, if I have the initial counter value which is there in C0, and if I want to decrypt C2, what I have to do is I have to treat C0 as the counter value, compute counter plus 2, invoke my underlying keyed function on the input counter plus 2, generate the pseudo random pad Y2 and XOR it from C2 which will give me back M2. So, depending upon my requirement I can decrypt any specific ciphertext block by just invoking one invocation of the underlying keyed function, which was not possible in the OFP mode. and more importantly we can prove formally that the stateful variant of the counter mode of operation is also CPA secure. That means, if I have a message M and for that my resultant ciphertext is C0, C1, C2, C3, where Y3 was the last pseudo random stream of pseudo random pad, and now I have a new message M dash, right. So, I do not need to pick a fresh counter value to generate the pseudo random stream of pad for the message M dash. I can use Y3 as the counter value for generating the next sequence of pseudo random pad for the message M dash, and the same can be done at the receiver end, and it can be proved formally that the stateful variant is also CPA secure. So, we have now almost exactly all the features that we require from a good mode of operation of the block cipher, and that is why this counter mode of operation is very popular, which is used in several instantiations of the real world protocols. Okay. So, now we want to do rigorous security analysis of the CPA security for this counter mode of operation, right. So, I am going to use this example. So, imagine a scenario where a sender has encrypted say a message consisting of 3 blocks, right, and this is how the counter mode of operation would have operated, and we want to prove that this counter mode of operation is CPA secure. So, before going into the actual security proof of the counter mode of operation, let us consider a variant of this counter mode of operation where everything remains as it is in the actual counter mode of operation, except that all the invocations of the keyed PRF are replaced by invocations of a truly random function, which is an unkeyed function. So, imagine both sender and receiver have agreed upon a truly random function, which is an unkeyed function mapping big L bit strings to big L bit strings. So, the variant of the counter mode of operation, which I denote as pi counter tilde, is almost the same as the actual counter mode of operation, except that all the invocations of the keyed function fk are replaced by the invocations of the truly random function little f. Now, what we are going to prove next is that if we consider this variant of the counter mode of operation based on truly random function, and if we consider any arbitrary polytime adversary participating in an instance of CPA indistinguishability game and makes total of qn number of encryption oracle queries, then the probability with which that adversary can win the CPA game is upper bounded by this quantity, right. So, if big L is actually if we assume that big L is some polynomial function of the security parameter, and anyhow q of n is a polynomial function of the security parameter, then overall we end up showing that the probability of any polytime adversary winning the CPA game against this truly random function based counter mode of operation is half plus negligible, which satisfies the definition of CPA security. So, let us first do that. Once we do this, later on we will actually show that the actual counter mode of operation, which we want to prove formally to be CPA secure, is not CPA secure, then it means that there exists a distinguisher who can distinguish apart the behavior of the keyed pseudo random function from the behavior of a truly random function, and which will be a contradiction to the assumption that the keyed function is a pseudo random function. So, that is the overall idea of the proof. We will first consider a variant of the truly counter mode of operation, prove it to be CPA secure formally, and then we will come back and argue that since the only difference between the actual counter mode of operation and the variant of the counter mode of operation is the underlying invocations of the function. So, the actual counter mode of operation should also be CPA secure, otherwise there is a distinguisher who can distinguish apart from the keyed function from the outcome of a truly random function, right. So, let us first proceed to prove the CPA security of the truly random function based counter mode of operation. So, consider an arbitrary computationally bounded adversary who participates in an instance of a CPA game, which will consist of 4 phases. We will have pre-challenge training phase, then we will have a challenge phase, right. And to answer the queries of the pre-challenge training phase, basically the challenger will select a truly random function which will not be known to the adversary, right, and all those queries will be encrypted by running the encryption algorithm of the truly random function based encryption process. And then once the pair of challenge plain text are submitted by the adversary, the challenger will pick one of those messages randomly for encryption and it will encrypt it by picking a random counter value which I denote as counter star, and then C star will be basically the value of the counter star or on the truly random function XORed with the message MB, and then there will be a post challenge training phase again where the adversary will adaptively submit encryption oracle queries and which will be encrypted as per this modified encryption process, and finally the adversary will output whether this challenge ciphertext is an encryption of message M0 or message M1, right. So, let us assume that the total number of queries which the adversary is asking throughout this instance of this experiment is Qn, where Q of n is some polynomial function of the security parameter little n. Moreover, we also assume that each query also consists of at most Qn number of blocks. So, actually we will assume the worst case scenario where there are total of Qn number of queries and each query is exactly consisting of Qn number of blocks, right. So, I denote the ith query for which the adversary has asked the encryption oracle service to be big M under I, and since big M under I consists of Qn number of blocks, to answer the encryption oracle service to encrypt this message big Mi, the challenger need to pick Qn number of counter values. So, I denote those counter values as counter I plus 1, counter I plus Qn and so on. So, the first observation is that if the adversary submits the message big M subscript I for encryption and sees the encryption of that message as per this variant of the counter mode of operation, then by seeing the ciphertext adversary will learn the value of the unknown truly random function on this counter values, namely counter I plus 1, counter I plus 2 and so on. Why? So, let us consider the ith query big Mi, which basically consists of Qn number of blocks, right, and for encrypting that message the challenger will pick a random counter value which I denote as counter subscript I, right, and once the counter value is selected, since there are Qn number of blocks in my message Mi, basically the challenger needs to evaluate the truly random function on counter I plus 1, counter I plus 2 and counter I plus Qn, which will generate the sequence of pad blocks which will be XORed with the actual message blocks that are present in the message Mi to generate the ciphertext blocks, and the whole ciphertext will be communicated back to the adversary as the response from the encryption oracle query. So, since the adversary will know the value of the counter I and counter I plus 1 and so on, the adversary just can simply perform this operation, namely it can XOR the jth ciphertext block and the jth message block present in the message Mi, and that will give him the value of the unknown truly random function on this counter value, namely counter I plus j, right. So, since I am assuming that my adversary is going to make Qn number of queries, those queries I am representing as message M1, M2 and M of Qn, and I am assuming that each of those messages further consist of Qn number of blocks, and assume that our challenger in this instance of the experiment uses this counter values for encrypting these message blocks, namely the first message is encrypted using the counter values counter 1 plus 1, counter 1 plus 2, counter 1 plus Qn and so on. So, these are the counter values which are used by the challenger, and as I have seen that based on the encryption of each message the adversary learns the corresponding output of the truly random function on the corresponding counter values. So, that means adversary basically have access to the value of the unknown truly random function little f on all the counter values which have been used by the challenger to respond to the encryption oracle queries. Now, our goal is to analyze what is the success probability of this adversary in identifying whether this challenge ciphertext is an encryption of the message M0 or whether it is an encryption of M1. And we can split this overall probability into the summation of two probabilities. So, consider the first case when the counter values which are used to prepare the challenge ciphertext C star are different from all the counter values which have been used to respond to the encryption oracle queries raised by the adversary. That is the first case. And the second event is when the counter values which are used to prepare the challenge ciphertext overlaps or gets repeated in at least one of the instances of the encryption oracle queries, namely the counter values which are used to prepare the challenge ciphertext overlaps with the counter values which have been used to respond to the adversary's encryption oracle queries. So, these are the two separate cases, and let us take the first case and try to analyze what is the probability that in that case adversary is able to win the CPA game, right. So, we are in the case when the counter values, namely counter star plus 1, counter star plus 2 and so on, which are actually used for encrypting the challenge plain text MB, are different from all the counter values which has been used to respond to adversary's encryption oracle queries, right. So, we are in this case. So, this is the challenge plain text MB encrypted by evaluating first the truly random function on these counter values, which have not been used so far in any of the encryption oracle queries to generate the pads, and those pads are XORed with the message blocks of the message MB to generate the ciphertext blocks. So, since this counter values counter star plus 1, counter star plus 2 and so on is never repeated, that means from the viewpoint of any adversary, the value of the truly random function on these new inputs which have never been used will be truly random, because that is what is the property of a truly random function. That means adversary does not know what are the pads which have been used to mask the blocks of the message MB. That means what we can say is that from the viewpoint of the adversary, his view is as good as if he has seen qn number of independent instances of OTP, namely the first block is encrypted by running an instance of OTP where the pad is completely unknown to the attacker. The second block of MB is encrypted again using a truly random pad which is unknown to the attacker, and similarly the last block of the message MB is encrypted by using a truly random pad unknown to the attacker. And as we have seen in the case of OTP, if the pads are truly random and unknown to the attacker, then it is perfectly indistinguishable or perfectly secure from the viewpoint of the attacker. That means, if the counter values which have been used for computing the challenge ciphertext is not repeated, then we can safely conclude that the probability that adversary wins the CPA game is upper bounded by 1 by 2. Now, let us take the second case when at least one of the counter values which has been used to encrypt any of the blocks of the message MB has been repeated or has been used to answer any of the adversary's encryption oracle queries, right. That is the second case, and we will now analyze what is the probability in that the adversary can win the CPA game in this case. So, for that let me consider an event overlap I. So, that is an event I am defining, and the event overlap I denotes the event that for when the challenger is encrypting the ith encryption oracle query from the adversary, then the counter values which are used for encrypting the blocks of the message MI gets overlapped with the counter values which have been used by the challenger to prepare the challenge ciphertext. So, that is what overlap I means. So, overlap 1 means the counter values which have been used for encrypting the blocks of the first encryption oracle query gets overlapped with the counter values used for encrypting the message block MB and so on. So, there could be several ways in which the event overlap I could occur, right. So, this is one possible way in which there could be an overlap between the counter values used for encrypting the blocks of the message MI and the blocks and the counter values which have been used to encrypt the blocks of the message MB. Namely, it could be possible that the last counter value which is used for encrypting the last block of the message MI is the same as the first counter value which is used to encrypt the first block of the challenge plain text. That could be one way in which overlap could occur, right. Or it could be possible that the first two counter values which have been used to encrypt the first two blocks of the challenge plain text overlaps or are same as the last two counter values which have been used to encrypt the last two blocks of the message MI. That could be one way in which overlap can occur, or it could be possible, continuing like this, if I analyze, it could be possible that another way in which overlap I could occur is that the first counter value which is used to encrypt the first block of the message MI overlaps or is same as the counter value which is used to encrypt the last block of my challenge plain text MB. So, these are the various ways in which the overlap I event can occur. So, let us understand the consequence of each of these cases, right. So, before going into the consequence, it should be clear to you that if at all the event overlap I occurs, that means there exists some indices j and j star such that the counter value which is used to encrypt the jth block in the message mi and the j star block in the message mb are same, and if this event occurs, then in this case the adversary can clearly win the CPA game with probability 1, because in this case the adversary will know the counter value which has been used to encrypt the jth block of the message mi, and adversary will see all the counter values which are actually used for encrypting the challenge plain text MB, because those counter values are part of the challenge ciphertext. So, as soon as the adversary sees that there is an overlap, then based on the value of the truly random function which it has already seen by seeing the response of the encryption oracle query, it can easily identify what has been encrypted in the challenge ciphertext, right. So, now we have to understand what exactly is the probability of the event overlap I happening. So, as I said earlier, the event overlap I can occur in several ways. So, if event overlap I occurs because of this case, namely the last counter value of which is used for encrypting the last block of the message mi is the same as the first counter value which has been used for encrypting the first block of the challenge plain text. If that is the way overlap I is occurring, that means that the value of the ith counter value should satisfy this relationship. Only if this happens, then the event overlap I could occur in this way, right. In the same way, if the overlap I occurs because of this condition, namely the last two counter values for the message mi and the first two counter values for the challenge plain text MB overlaps, if that is the way overlap I is occurring, that implies that the value of the counter I should satisfy this relationship. And in the same way, if I consider the scenario where the event overlap I occurs because of the fact that the last counter value used for encrypting the last block of the challenge plain text overlaps with the first counter value used for the encrypting the first block of the message mi, then for that case the counter I should satisfy this relationship. So, these are the various ways in which the event overlap I could occur. That means, I can say that the probability of the event overlap I to happen is the same as the counter value I which is used to encrypt the ith encryption oracle query follows in this range. It should fall in this any of this, it should lie in this range. If it lies in any of this range, then the event overlap I could occur. Now, it is easy to see that what is the size of this range. I can always upper bound the size of this range to be 2 times qn, and since each of the counter values which are used in the modified counter mode of operation is selected uniformly randomly from the set of big L bit strings, that is why I can say that the probability of event overlap I to occur is always upper bounded by this quantity, right. So, that is the way event overlap I could occur. Now, our goal is to analyze that what is the probability that the counter values which are used for encrypting the challenge plain text gets repeated in any of the qn number of queries. So, remember adversary had made qn number of queries where each query actually consists of qn number of blocks, and whatever we have analyzed till now was with respect to only one specific query, namely the encryption oracle query for the ith message. So, it is easy to apply the union rule here, because each of these queries encryption oracle queries are independently answered by the challenger. So, if I apply the sum rule, I get that the probability that the event overlap occurs. So, now the event overlap is defined to be the event that any of the counter values used for encrypting any of the blocks of the challenge plain text gets repeated while answering any of the qn number of encryption oracle queries. So, I can apply the sum rule, right, and by sum rule I get that the probability that the event overlap occurs can be upper bounded by this quantity. So, now coming back to the answer, that what is the probability of adversary winning the CPA game against the truly random function based encryption process. So, as I said earlier, it could be divided into two cases, whether the counter value used for encrypting the challenge plain text gets repeated or not. So, the case so overall I can say that the probability that adversary wins the CPA game against the truly random function based encryption process can be written as the sum of two individual probabilities. So, this is the case when the event overlap does not occur, that means the event that the counter values that is used for encrypting the challenge plain text never gets repeated, but still the adversary wins the CPA game. And the second probability is the probability of adversary winning the CPA game under the condition that overlap occurs has occurred, right. That means, one of the counter value has been repeated. Now, it is easy to upper bound the first probability here as the probability of it is always possible to upper bound the second probability here by the probability of the event overlap being occurring, right. So, I am simply applying simple rules of probability here. The first probability term is retained as it is, and now we know both the terms here, the value of both the terms here. The first probability is basically we have computed to be 1 by 2 plus 2 q n square by 2 power l, right. The first probability is 1 by 2, because if the event overlap does not occur, then we are then the situation is same as in the case of q n number of independent instances of OTP, in which case we know that the probability of adversary winning the CPA game is 1 by 2, and the probability of overlap we have already computed to be this quantity. So, that is the maximum probability with which our adversary can win the CPA game against a truly random function based CTR mode of operation. So, this part is done, we have analyzed this, but our actual goal is to show that the pseudo random function based counter mode of operation is CPA secure. So, what we are going to do now is we are going to prove that if my underlying keyed function f k is a secure PRF, then the absolute difference in the winning probability of the adversary absolute difference of the adversary winning the CPA game against the counter mode against the PRF mode against the PRF function based counter mode of operation and the truly random function based counter mode of operation can be upper bounded by a negligible quantity. That is what our next goal is. So, this will follow more or less using the same argument that we had used to prove the CPA security of our first candidate CPA secure scheme based on the pseudo random function, right. So, remember in that proof we had first considered a hypothetical truly random function based construction, proved its CPA security, and then we gave a reduction based argument where we showed that the difference in the winning advantage of the adversary between the two instances of the CPA game is upper bounded by a negligible probability if my underlying function is a pseudo random function. So, we can use the same or similar argument and end up showing that the difference in the adversary winning the CPA game against the actual counter mode of operation and the adversary winning the CPA game against the truly random function based counter mode of operation can be upper bounded by a negligible quantity. And since we know that the adversary winning the CPA game against the counter mode of operation is this 1 by 2 plus 2 q n square by 2 power l, by reshuffling the term we end up getting that the counter mode of operation using the pseudo random function is also CPA secure, right. So, that is what we end up showing, and which concludes that the counter mode of operation is actually CPA secure. So, that brings me to the end of this lecture. To summarize, in this lecture we had seen two of the modes of operation, namely OFP mode and counter mode of operation, and we had also seen the security proof of the counter mode of operation. The counter mode of operation have several attractive features, namely the encryption and the decryption can happen in parallel, and we do not require any sophisticated assumption from the underlying keyed function. It is enough or it suffices for the underlying keyed function to be just a pseudo random function, and the stateful variant is also CPA secure, and these attractive features make the counter mode of operation to be used rigorously in the real world protocol. Thank you.